So my name is B. Ravindar, Assistant Professor in the Department of Electrical Electronic Engineering, BVRIT Narsapur. Today I am going to discuss on Power System 2 in a topic is symmetrical components. So in this content, we can see that symmetrical component theory in this particular unit, symmetrical component transformation. And in that, we need to see about positive, negative, zero sequence components, voltage, current, and impedances, and sequence networks like positive sequence network, negative sequence, and zero sequence networks, and numerical problems on this. And next topic we can cover on fault analysis. The first one is LG fault, double L fault, double LG fault, and triple L and triple LG fault. And this fault without impedance also we can study, and with fault with impedance we need to study. Next is some problems on this various fault analysis in a power system network we need to study. First is what is the symmetrical component analysis. In this we can say it is easy to analyze the three-phase systems having balanced symmetrical voltage and balanced current. So basically we have the power system network. It may be so that this power system network we can represent, if it is a balanced system, we need to study the fault analysis in a single network. So because it is a balance, so single network, single equation is easy, then we can easily calculate the fault analysis if the system is. So if the system is balanced, it is easy to represent the fault analysis in a single circuit. So if the fault analysis in a single circuit is possible if it is a balanced. So the time is very easy to calculate this analysis. If the fault, if the system is balanced, we can easily calculate the whatever the fault analysis it is there. And because of balanced vector, the analysis of single phase circuit leads directly to a three-phase circuit solution, but the situation becomes complex if the voltage current vector in the three-phase circuit becomes unbalanced. If the system is unbalanced system, it means if there is a fault is occurred, then the system become unbalanced. To study such a unbalanced system, we require three equations, then the time taking is very high. And in case it is not easy to apply your KCL or KVL in that three-phase circuits, and the unbalanced voltage current vectors are developed due to this unbalanced load or unbalanced faults in the power system, such as single line to ground or any double L fault like that. So an unbalanced system of n related vector can be resolved into n system of balanced vector called symmetrical component of original vectors. And the symmetrical component of three-phase systems, the three unbalanced vector, either say VA, VB, VC or IA, IB, IC, can be resolved into a three balanced system vectors. So this VA, VB, VC and IA, IB, IC are the unbalanced vectors. So when the system is unbalanced, means there is a load variation will be there, or it may be some fault, then the system become unbalanced. Then the voltage, whatever say A phase, B phase, C phase, this voltage or currents may becomes unbalanced. So in order to study this unbalanced quantities, we require three equations, then time taking is more. So resolve this three balanced system vector. The vector of these balanced systems are called symmetrical components of original system. So in order to study this type of system, we require a symmetrical component in order to study this unbalanced vectors. So the symmetrical component of three-phase systems as follows. One is maybe positive sequence component. So in order to study this unbalanced quantities, we have the positive sequence component, and that we can represent as 1. With a notation, and the negative sequence component we can represent as 2, and zero sequence component we need to represent as 0. Okay, so 1, 2, 0. Positive sequence is 1, negative sequence is 2, zero sequence is 0. So this positive sequence, what is this positive sequence component means? So means this positive negative sequence component, this unbalanced quantity whatever we are having, we are representing with a symmetrical means this symmetrical components. And then we are having this positive sequence component, negative 0, 3 sequence component. It is a symmetrical components. So this positive sequence component is having a equal in magnitude. So the positive sequence is equal in magnitude, and it is having 120-degree phase angle exists with the same phase sequence of original vector. So it is having 120-degree phase displacement. So means say R phase, your A phase. So it is a phase sequence. We can see that it is say R phase or A phase, R, Y, B, three phases. So all are displaced by 120 degrees. 120 degrees displacement. So what is the first point? Equal in magnitude. All these quantities are equal in magnitude. Magnitude wise it is same, and also 120 degrees displacement. These quantities R, Y, B phases, it may be voltage or current. These components are having equal magnitude and 120 degree displacement, and it will be exist with the same phase sequence of original vector. So whatever the original vector is there, it will be same. Then we are saying that it is a positive sequence component, and this positive sequence component will be exist before and after the fault. So you can see that this basically our synchronous generator, the rotor is coupled with the your stator. So whenever this rotor is rotates, means the turbine, this rotor is connected to the turbine, and when the turbine rotates, rotor rotates, then this rotor cuts the flux, then EMF is induced in the stator, and there is a current flow takes place like this. Okay, so this due to this EMF we are having the flux here, and this flux, then we are having a pi r, then we are having a EMF induced EMF here, R or maybe A phase ER. So like that we are inducing the EMF in the stator terminal, and if there is a fault occurred, some fault is there. So if the fault is occurred, then the particular positive sequence component will also exist, even though it is before fault and after the fault. After fault also this positive sequence component gets exist. And what is the significance of positive sequence component? So what we are seeing, that positive sequence component means it is a equal in magnitude, 120 degree phase displacement, and this particular having the same phase sequence of original vector. It is same phase sequence of original vector, and it will be occur before and after the fault. Okay, say you can see the positive and negative sequence, it is only during the fault condition it will exist, but this positive sequence component will be exist during and after the fault also exist. So then what is the significance of this positive sequence component? So the relay and circuit breaker operate on positive sequence component. So you can see your say alternator, it is having say EMF induced in that. So this is alternator. At this alternator we need to connect a CT, then it is having circuit breaker, some relay mechanism will be there like this. So it will be tripped based on this circuit breaker and CTs, like this it is there. So we can see that relay and circuit breaker, this is your relay and the circuit breaker operate on positive sequence component. So this positive sequence component exist before and after the fault. So before fault and after the fault, this particular positive sequences exist. So that in order to select a this circuit breaker or relay ratings, we need to decide based on this positive sequence component. So this fault analysis, positive sequence component help in analyzing the symmetrical fault, where the fault impedance is the same in all the three phases. So in case of fault analysis it is required. Next is in stability studies, the positive sequence commuter vital in stability analysis, particular for synchronous machines. So what is the machine, it is in a stable, means it is in a stable or not, we need to study in the stability studies. Or it may be a protection coordinate, that is help in the designing the protective relay systems that can be accurately detect the fault while discriminating against normal system disturbances. So whenever this pickup of this relay, pickup of this relay, they can set as 1.2 times of this fault current. or this positive sequence component. If the positive sequence component is exists before and after fault, and this positive sequence component exceed this 1.2, then the relay will be sensed and the circuit breaker can be tripped. So that is a pickup value we need to set to the circuit breaker. And the equipment sizing and rating. The positive sequence component aid in determining the appropriate sizing and rating of power system equipment like transformer, cable and generator that can also decide by this positive sequence component. These are the major significance of positive sequence component. That is, we can see the relay and circuit breakers operate on this, and fault analysis, stability studies, protection coordinate, or equipment sizing and rating. There we can utilize this positive sequence component. And next one is about a negative sequence component. So this, whenever the direction of rotation of the stator flux, so you can see in case of this positive sequence component, so whatever the flux here, this before the fault, the flux rotation is clockwise. After the fault is occurred, then also it is a clockwise. Means the positive sequence component will be in rotation as whatever the actual the rotor flux is there, thus it will be same, clockwise rotation will be there. But in case of this negative sequence component, you can see, so whenever the direction of rotation of stator flux is the stator flux opposite to that of direction of rotation of rotor flux. So the stator flux is opposite to the rotor flux. The corresponding electrical quantity is called as negative sequence component. So in this negative sequence component, the flux, whatever the induced in the rotor and the stator, both are in opposite. So you can see the flux which is here, whenever there is a fault, then there is a pi A2 means it is a the negative sequence component of flux. This flux, it is a rotor flux, and this pi A2 is a opposite flux. Anti-clockwise rotation of this flux will be exist. And we know that the synchronous speed will be rotated at a speed of ns, and this is, it is a pi is ns, and this pi A2 means this negative sequence component flux will be rotate with as ns minus of ns. Okay, it is ns, it is also ns, but it is an opposite. So minus of minus ns. So 2 times of ns. The relative speed is 2 times of ns, and then corresponding frequency is 2f. And ns is nothing but, we can see that ns is 120f by p, means the ns is proportional to frequency. So ns is double frequency, then it is 2 times of frequency. Due to this rotor winding, circulating current will be exist. So due to this higher flux, so higher frequency of flux, there is a circulating current is exist in the rotor winding. Rotor winding is heated, so we can protect by the negative sequence relay. So then the rotor winding will be heated, and there is a possibility of that the winding can be break. So in order to protect from this rotor winding, we require the relay. That relay is called negative sequence relay. Negative sequence relay. So this negative sequence relay will be provided for a synchronous generator. So negative sequence component of this one, it is having this negative sequence component will having equal in magnitude. So it is similar what we are saying that. So this negative sequence component is having say VR, R phase, Y phase and B phase. So we can see that it is having 120 degrees displacement. All are 120 degrees displacement, equal in magnitude, but opposite of 120 degree phase angle exists, but opposite phase sequence of original. Original is having like this R, Y, B. It is a original sequence. Now we are saying that R, B, Y. So opposite phase sequence will be there in case of a negative sequence component. And occurs only during the fault. This negative sequence component will occurs only during the fault conditions. So means the positive sequence will be exist during and before the fault also there, but this negative sequence will exist only during fault. And what is the significance of this negative sequence component is, so synchronous generator is protected from the unbalanced condition by using negative sequence relay. So we have the negative sequence relay to protect the rotor winding by having a high heating. Next, another component we are having is zero sequence component. So we can see that this zero sequence component will exist the fault, there is a fault and that fault is a neutral fault, grounded fault. If it is not a grounded fault, this zero sequence component will not exist. So you can see that there is a fault, three-phase fault, and it is connected to ground. So now, and this particular generator also need to connect it to ground. It is a solid ground. So we have the different type of grounding. So reactance grounding, resistance grounding, and solid grounding. So here solid grounding, then only the current path flow will be takes place. If there is no neutral of this solid grounding, there is no possibility of this circulation current will not exist from this fault point to that particular point. So in every unbalanced condition, there will be a negative sequence component, but there may not be a zero sequence component. So you can see that during unbalanced condition, so if the system is unbalanced means it may be fault or maybe this RYB phases may be unbalanced. So during unbalanced condition, we may have the negative sequence component, but zero sequence component may not exist. Zero sequence component is exist if the system is faulted and it should be grounded. And the zero sequence component exists in following condition: the fault must be a grounded fault. The fault must be a grounded fault. It should be a grounded fault, and nearest to the neutral must be grounded. So this your particular alternator, it should be connected to the ground. Otherwise, there is no possibility of this zero sequence component to that particular point. If a transformer is there or transmission line is like this, there is a transmission line and there is a transformer, and if the fault is occurred here like this, and this transformer is having a star grounded like this, then it is a possible that the fault current will flow like this. But if it is having both are delta delta, so like this delta delta, then there is no possibility of flowing of this fault current. So fault current will not flow if it is having delta delta. It should need some grounding, then only this particular zero sequence component will be exist. And this zero sequence component is having equal in magnitude, then no phase displacement. So equal in magnitude means these magnitudes are R, Y, B phases, VR, VY, VB. All these three phases are having equal magnitude and no phase displacement, zero phase displacement. Okay, no phase displacement, and occur only when the neutral is grounded and fault occurred with the grounded. So you can see that neutral is grounded and the fault occurrence is with the grounded. And this important of zero sequence. Why this zero sequence is, what is the significance of this? So zero sequence components are used in the calculation of leakage flux. So for calculation of leakage flux, this zero sequence component is needed. So the flux produced by zero sequence component are equal in magnitude without any phase displacement, and hence this flux does not have any armature reaction effect. So there is no having any phase displacement, so that there is no armature reaction effect to the influence the rotor flux. So it does not affect on the rotor flux, so that this component will be in the form of leakage component in the stator winding. So it does not affect from the stator to rotor. It does not affect on the rotor flux. So this particular zero sequence component we can say as a leakage flux. And hence the zero sequence component is also called as leakage component. It is also called as leakage components. So you can see that positive sequence component, say A, B, C. So we are taking the notation either ABC or RYB. So VA1, VB1, VC1 with a displacement of 120 degrees. That is a positive sequence component. Negative sequence, you can see the VA2, VB2, VC2. So here it is says VA1, VC1 and VB1. So we can see that the A, B, C. But here we can see that VA2, VB2 and VC2. So it is an opposite, means it is a VA2 and VB2 are not in same sequence. It is a the negative sequence component are opposite. And zero sequence component we can say VA0, VB0 and VC0, and it is having equal in magnitude. So we are representing the positive sequence component with a VA1 with a 1, here negative sequence component with a 2, zero sequence component with a 0. So this the operator A, next we can see about operator A, and this operator A is nothing but cos 120, and this 1 at an angle of 120, that we can represent it as cos 120 plus j sin 120, that we get as minus 0.5 plus j 0.866, and a square a cube, and this 1 plus a square equal to 0. So what is balanced symmetrical symmetrical three-phase vector? So we can see that it is, say, A phase, B phase and C phase, and we are assuming that it is 100 or maybe a 230 voltage or 440 voltage at an angle 0, and 440 at an angle minus 120, 440 at an angle 120, means we can see that magnitude is same. These are magnitude is same, but phase displaced by 120 degrees. So minus plus 120, 240, like that we write, or like this. So you can see the three phase, this phase sequence, we can see that R phase is having like this, it is R phase, and it is a or Y phase, or A phase, B phase and C phase. All are displaced 120 degrees each. And we can say unbalanced systems. So unbalanced system means it is not having equal magnitude. You can see here 80 at an angle 0, and it is having a 50 at an angle 210, and 120 at an angle 150. It is having different magnitudes and phase angles. So then we can say the system becomes unbalanced. So in case of unbalanced, this magnitude, you can see the A phase is like this, and B phase is having lesser. So like that we are having, and this C phase is having 150 degrees. So magnitude is higher in case of C phase. So we are taking the phase sequence is ABC. So this particular phase sequence is introduced by D.L. Fortescue in 1918. First suggested a method of symmetrical component to all such complex problem of unbalanced three-phase system. So he showed that any unbalanced asymmetrical three-phase voltage or current vector can be broken into a three component which are called balanced symmetrical component. So this unbalanced asymmetrical component can be resolved into a three-phase balanced vector, and these three symmetrical components are called positive sequence, negative sequence and zero sequence component. So we need to analyze this unbalanced quantity. We are taking a positive, negative and zero sequence components. So this unbalanced vector, we are saying that it is a phase and B phase, C phase. It is having different magnitude and phase sequence, but this balanced positive sequence component, positive, negative, zero sequence are called symmetrical components. These are the unsymmetrical components or unbalanced vectors. Now the balanced vector with a positive sequence, we can see that it is having VA1, VB1, VC1. All are same magnitude and 120 degrees displacement. These are 120 degrees displacement. And the negative sequence component, we are having like this VA2, VB2 and VC2. So it is having again 120 degrees displacement, but opposite to the original phase sequence. And zero sequence of a balanced vector, it is having all are in a same magnitude and there is no phase displacement. Phase displacement here it is, phase displacement is 0. So that is the case in case of zero sequence component. So you can see the sequence component in case of positive sequence, we are saying that VA, VB, VC, VA1, VB1, VC1, and in case of negative sequence VA2, VB2 and VC2, and in case of zero sequence we are writing as VA0, VB0, VC0. Now we can see that VA equal to VA0 is this unbalanced vector. So VA is an unbalanced vector and VA0 is a this particular vector. We are saying that in order to calculate the VA, this VA is nothing but, so VA0 plus VA1 plus and this VA2. So these three are added. So VA equal to nothing but VA0 plus VA1 plus VA2. Next we can see that VB is nothing but this unbalanced vector. VB is nothing but this VB0 and VB2 plus VB1 plus VB2, and VC is equal to VC0 plus VC1 plus VC2. So means all these three components, positive sequence plus negative sequence plus zero sequence, we are adding. Now we can see that this VA, VB, VC are three unbalanced vector. So VA, VB, VC are the unbalanced vector, and VA0, VA1, VA2 are the balanced vector, and these are symmetrical components, are also called as balanced components. These are, so we can see V0, VA0, VA1, VA2, VB0, VB1, VB2, VC0, VC1, VC2, and this total we are having 9 component of this symmetrical component, and these are called balanced components. So we are representing unbalanced quantities in terms of this balanced symmetrical components. So we can say, in order to reduce this number of symmetrical components, it is proposed to replace this. So we are seeing that VA0, VA1, so total 9 this symmetrical component we are having, but if you reduce this 9 symmetrical component in a single quantity, so the symmetrical component of B and C phase in terms of phase by using a suitable notation which is denoted by operator A. So means this phases B and C also we need to represent with respect to A0, A1, A2, then it is very easy to analyze the system. So if you are having like that, if it is having unbalanced quantities, to analyze the unbalanced quantities it takes more time. So in order to reduce the time, we need to go for symmetrical component. So that symmetrical component, again, it is having for each phase having a different things, then we need to represent with a operator called A or alpha. We are having with respect to the operator, we need to represent this VB0, VB1, VB2 or VC0, VC1, VC2 in terms of this VA0, VA1, VA2. So all this B phase also represent with A phase, and this also represent with the A phase. Now we can see that how we can calculate this VA equal to nothing but. So we are getting that VA equal to VA0, VA1, VA2. So VA0 means this one. So we can see that VA0 means this vector. It is the VA0. Okay. And next one is VA0 plus VA1. VA1 means it is like this. So VA1 after this, say 90, it is your VA1. After VA1, VA0 plus VA1 plus VA2. So VA2 is like this quantity. So this is the VA2. So sum of this, all these three, it is your VA. So VA0 plus VA1 plus VA2 is nothing but VA. Similarly, we can calculate VA0, this VB0. So it is your VA0 as well as VB0, VC0, same magnitude and there is no phase displacement. Then VB0 plus, so it is VA1, VB1 means like this. This is a VB1. So we need to represent as VB1 is like this. And that is the VB1 and corresponding VB2 is here like this. So VB2 is like this. And resultant of these three quantities, VB0 plus VB1 plus this VB2 equal to nothing but phase VB. So we are getting as VB. Similarly, we need to write this VC0 means again same. It is your VC0 plus this VC1 is nothing but this one. It is a VC1. So means we need to represent as, so this component is VC1. Next we can see that VC2 means this one, this component. So it is your VC2. So VC1 plus VC2 plus VC0 plus VC1 plus VC2. This resultant is your phase VC. So you can see that it is your A phase, it is the B phase and it is your C phase. So it is having different magnitudes. So VA is having higher magnitude, VB is somewhat less and VC. Like that it is having, it is a unbalanced quantities. So like that we need to represent this unbalanced electrical quantity VA, VB, VC in terms of symmetrical components. So this we see in the summary of this positive negative zero sequence component. The positive sequence is having equal phase magnitude, but negative sequence also equal in magnitude, zero sequence also in equal in magnitude. And positive sequence is having 120-degree displacement, negative also 120-degree displacement, zero sequence is having no phase displacement. And positive sequence is same phase sequence as the original system. So original whatever it is there, the same phase sequence we can see in case of positive sequence, but in negative sequence it is opposite phase sequence as the original vector. And this zero sequence, there is no phase sequence. And in case of same phase rotation as the system phasor, here the same phase rotation as a system phasor and same phase rotation as system phasor. So next, what you can see, that operator A, how this operator A can be utilized, used in case of this unbalanced electrical quantity can be represented with the symmetrical quantities. And that symmetrical quantities we need to represent with respect to A phase or B phase, C phase. Then we can see the operator which rotate a given phasor by 120 degrees in the positive direction, that is a counter clockwise direction. And the letter of A is used to designated such as a complex operator of a unit magnitude with a angle of 120 degrees. So this operator can be represented as 1 at an angle 120 degrees. Either we can represent it operator A, or some books they can represent K, alpha, like that. We are having different notations to represent this operator A. So that is your A is nothing but A equal to 1 at an angle 120 degrees. So you can see that R phase, Y phase, this Y phase and B phase, all are rotating with respect to this. We can see that operator is rotating 120 degrees in anti-clockwise direction. Anti-clockwise direction. So we can see that A is nothing but 1 at an angle 120, and that we are writing as minus 0.5. 1 at an angle 120. So it is a 120 degrees. So 120 degrees is nothing but minus 0.5 j 0.86, minus 0.5 on this x-axis and plus j 0.86 is so it is an imaginary axis. Then we are getting at this point. Similarly, A square means 1 at angle 120 into 1 at angle 120, that is minus 0.5 minus j 0.866. Minus j 0.5 and minus 0.866 means this point. It is the angle 120. After 120 we can get this point. It is another 120. Further AQ is nothing but 1 at angle 120, 1 angle 120, 1 angle 120. Means again we are coming to the original vector and it will become 1. So adding of these quantities, 1 plus A square. 1 plus A means it is minus 0.5. 1 minus 0.5 plus j 0.866, and A square means we are saying that minus 0.5 and minus 0.866 j. Then you can see that 0.866 cancel, 0.5 minus 0.5 again 1 get cancelled, then you can get 0. So means the 1 plus A square equal to 0 and A cube is 1. So the purpose of this symmetric component is to reduce the time taking. So main the thing we required this symmetrical component is to reduce the time taken by analyzing these unbalanced quantities. So this operator we can see with a, having equal magnitude and anti-clockwise direction it can be rotated. So this also we can write as A equal to nothing but equal to e power minus j 120, like that also you can write. Or so that 120 means cos 120 plus j sin 120, we can get this one, and A square and A cube is 1. And what does this operator can do? So it is multiply with any vector, then the vector will rotate in 120 degrees anti-clockwise. So any vector we can represent and it can be rotated at the angle of 120 degrees angle. Suppose if you are taking this is a reference, so V at an angle 0, and so it is a 120 degrees, and if you want to represent this particular vector with respect to this one, means this angle is V at an angle 120 degrees. So means this 1 at angle 120 degrees means it is a into V. So it is a vector. Similarly, it is a 240 degrees. 240 degrees means again 120, then it is A square times of V. So you can see that V is the reference, we are saying that. So this V, now it is rotating with respect to this operator A with a 120 degrees. Like that for M angle, M at an angle theta degrees, then M at an angle of theta plus 120 degrees or 240 degrees. 1 at angle 240 degrees. Thank you. So today we learn about on this symmetrical components. What are the symmetrical component is there and how it can be analyzed this unbalanced quantity into balanced quantities. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.